we are looking at lesson 6.4, which is about rational exponents. So if you remember, rational numbers are numbers that can be written as fractions. So we're basically looking for exponents that might be in fraction form and what that actually means. So here it says the nth root of a. So a is our base, okay? And if we're looking at m over n as the exponent, then this can actually be written in radical form where a is the radicand. M, just like an exponent normally, is still an exponent, and it could be inside the radical, or it could be outside the radical. And n is representative of the index of the root that you are taking. So when you see a fraction exponent, this is what it actually means. The calculations that you're doing are related to radicals and roots. So this property chart just represents the stuff that you see in your book. All the normal properties still pertain to fractional exponents, the same way that they do of any other exponent. So like right here, a to the m times a to the n, you add the exponents. You still do that. You're just adding fractions and getting your result from there. So we're still going to use these that same way. All right, so when we look at examples, when I think about 625 to the 1/4, what I'm really thinking to calculate that answer is what is the fourth root of 625. So if you're unsure, you could break down 625. It's 25 times 25, 5 times 5 times 5 times 5. So it turns out that this is equal to just 5. Okay, so 625 to the 1/4 power is the same as 5. Now in part B, we see 12 to the 1/2 times 12 to the 1/2. So just like previously with your exponent rules, if you have a base that's the same, you can keep the base and take the exponents and add them together. And in this case, 1/2 plus 1/2 will make 1, and 12 to the first power is just 12. In part C, you see a problem where we have not the same bases. However, we do have the same exponent. So if we think about what this problem might look like if that exponent had not been distributed, we would have our 12 times our 18 and the 1/3 here. Then we can multiply 12 times 18. Okay? And when we do that, sorry, no calculator on B. We get 216 to the 1/3 power. Now that may look simplified, but you have to ask yourself, do you know what 216 to the 1/3 power is? Which really means the cube root of 216. And if we break down 216, it turns out that there is a group of 3 6s. So 6 would be the cube root of 216. I want you guys to think of some questions. What if the problem looks like this? And bring it to class with you tomorrow. And we're going to actually look at your what if scenarios, when we can simplify, when we can't simplify, and try to answer any questions you have about how a fractional exponent might work. Okay, so here we're going to rewrite the expressions in radical form. Okay? So notice here that negative 2y is the base, and 4/5 is the exponent. And remember that the denominator of the exponent is the index of the radical. So negative 2y to the 4th. Okay? So we could even write this as the 5th root of 16y to the 4th. And that would be this expression in radical form. For part 2 here, we see d to the negative 3/2. So negative exponents work how they always have. If you want the exponent to be rewritten in a form where it's positive, you rewrite it so that you have the reciprocal of the previous expression. So d is now in the denominator with a positive 3/2 exponent. Now that exponent really means that this is d to the 3rd power, and we're taking the square root of that, which is 1 over d rad d. We need to rationalize the denominator. So we will multiply by the square root of d, which will then give us the square root of d over d to the 2nd power. So there's what each of those would look like written in radical form. Now we should be able to work the other direction also, which is to take a radical and write it in exponential form. So here, a times b to the third is all the radicand, or inside the radical, and because the index of the radical is a square root, or index of 2, we would use 1/2. So this would give us a to the 1/2 power and b to the 3/2 power. In the second problem, w squared is our radicand. That's all being raised to a power of 1 over whatever the index of the radical is, which is 3, which would then give us w to the 2/3 power. So this is how we would rewrite radicals into exponential form. All right, now we're going to look at some expressions and see if we can simplify them. So if you look at part A, we had talked before about the fact that their indexes weren't the same, therefore we didn't feel like we could simplify this expression. But now if I rewrite this in exponential form, so I'm going to rewrite these radicals with exponents instead, I now see that they have the same base, and what I can do is I can go ahead and I can add together the exponents. So 1/6 plus 1/3, for those of you that struggle with fractions, we would turn the 1/3 into 2/6, which would give us 3/6, which simplifies to be 1/2. So this is really like 10 to the 1/2 power, or the square root of 10. And it was given to me in radical form, so I'm going to go ahead and write my answer in radical form. Now in part B, you might see this as simple. 64, 4th root of 64. If you break down 64, we have 8 times 8, 4 times 2, and 4 times 2, 2 times 2, and 2 times 2. So we do have a 2. So you might think, well, you know what? We have 2, and then we have the 4th root of, and I'm sorry, that shouldn't say 2. It should say 4, because there are 2 factors left of 2 when we simplify the radical, so this should say 4. Okay? So you might think, well, this is the most simplified version. But actually, this isn't, and we could look at the problem from the beginning or from the 4th root of 4. If you write 64, 4th root in exponential form, what you can do is, if 64 is a perfect square, a perfect cube, try rewriting it any way you can that might help. So there's a couple options for 64. 64 is a perfect square, 8 squared to the 1/4 power. And it's also a perfect cube, which is 4 cubed to the 1/4 power. Now, I'm not going to continue to pursue this 4 cubed option, because if I multiply together the exponents there on 4, I'm just going to get 3/4, which doesn't reduce. However, with the 8 here, if I multiply together the exponents that are on 8, I will actually have 8 to the 2/4 power, which is the same thing as 8 to the 1/2 power. So I get here that this expression could be 8 to the 1/2 power. So I'm going to write that over here, and then we'll talk about turning it back into radical form in a minute. If I had simplified first, like we did right here with the 2 and the 4th root of 4, the way that I would see this is there's 2 times 4 to the 1/4 power. And then again, 4 can be rewritten as 2 to the 2nd power. So the only time I'm trying to simplify like this is when this number in here is a special number, a square, or a cube. And if I do rewrite it, these exponents multiply and simplify. So instead of 2 to the 2/4 times 2, I get 2 to the 1/2 times 2. And so again, since the problem was given to us in a radical form, we're going to go ahead and go back and write each of these in radical form. So here, 2 times 2 to the 1/2 is 2 times the square root of 2. So there's our answer if we did it this route. If we had done it from the 8 to the 1/2 power, this is the square root of 8, which then if we break it down, we get 2 times the square root of 2. So notice that either way, I get to the point that the 4th root of 64 is the same thing as 2 times the square root of 2. Just kind of using this idea that I can rewrite this number in different ways. So like 64 became 8 squared or 4 became 2 squared, if that helps me simplify the exponent. All right, so again, what is each number in simplest form? We're going to try and break these down. So we have negative 64, and then given the exponent's a fraction, I know that I'm looking at a square root. 3 is the index of the radical. And then 5 can either be applied to the 64 before or after I take the cube root. I personally, in this problem, am going to think about applying the 5 after I take the cube root, because 64 to the 5th power is going to be a really large number, plus the cube root of 64 is 4, so I know that already. So this is going to be negative 4 to the 5th power. And so then negative 4 taken to the 5th power, so 256 times 4, 22 is 1,024. Right, and then I have 32 to the negative 1.2 power, and I'm actually going to think of negative 1.2 as a fraction since I'm well equipped now to deal with fraction exponents. So this is 1 and 2/10, or 1 and 1/5, which is negative 6/5. So I'm going to think of this as 32, try this again. 32 to the negative 6/5 power. So this means I'm going to take the 5th root. Rewind. All right. Because of the negative, I'm first going to rewrite it as 1 over 32 to the 6/5. Then I'm going to work with my 32 to the 6/5, understanding that that's the 5th root of 32 and raised to the 6th power. The 5th root of 32 is 2, so I'm going to do the root before the power. So I'm going to get 1 over 2 to the 6th power. And 2 to the 6th power is 64. So I'm going to have 1 over 64 as my final result. So normal exponent rules, negative means we use the reciprocal, but just understanding that 6/5 means the 5th root and the 6th power. All right, so the last thing we're going to do is simplify each expression that's here. So in this first one, I'm actually going to write the x with a 1/2 exponent. And the reason I'm doing that is because there's this 3/2 exponent out here. And so I want to be able to combine everything together. So I'm just going to give that exponent to each of these. And then x is going to be to the power of 3/4 because of those multiplying together. Okay. So 9 to the 3/2 power means the square root of 9 cubed, which is 3. Okay. Oh, sorry. The square root of 9 is 3, and then we have to cube it, so we're going to get 27. Now, y to the 3/2 means the square root of y being raised to the 3rd power. So that means 1y outside the radical and 1y inside the radical. But here's where I have a problem. This y is inside of a square root, but when I look ahead at x, it's going to be inside a 4th root. So if I really want to write this as simple as possible, I want them to all be in the same radical. So I'm going to keep my 27 since it's outside the radical, and I'm going to think about how I could put both the x and the y with their different exponents in the same radical. And that would be by making a common denominator so the radicals have the same index. So I am going to rewrite the exponent on y with a denominator of 4, which means this is going to become 6. Okay? So that I can write in the 4th root that I have y to the 6th power and x to the 3rd power. And now I'm still going to simplify that a little bit because this y to the 6th power right here, we can take some 4th root of that. So my final answer is going to be 27. And I'm going to have the because the y's can simplify, I'm going to be able to take out one group of 4 y's. And it's going to leave y squared and x cubed. And I'm not going to simplify the y squared even though the fourth index and the squared power might help reduce, because I want the y and x in the same radical. So that's how we would simplify that. Okay? In exponential form, the simplest way to write this would be 27. You had your y to the 3/2 power and x to the 3/4 power. All right, so now we're going to look at the same thing for the next problem. First of all, it's a negative 1/3, so I'm going to think of everything as 1 over 27 x to the 6th, y to the 9th to the positive 1/3. And then I'm going to use this exponent with each factor in the parentheses. So 27 to the 1/3, x to the 6/3, and y to the 9/3, which is going to simplify to be the cube root of 27, which is 3, x to the 6/3, which is really x to the 2nd, and y to the 9/3, which is really y to the 3rd power. And that's it. So your goal is just going to be to simplify these as much as possible, making sure that you realize that rational exponents can be used with normal exponent rules and can help you represent radicals in a different way.